This is an extended version of a talk I gave in the summer on at the conference Thermodynamics 2.0, which is a good group, and they have another conference. If anybody's interested in that stuff, just so you're trying to. My mouse is not behaving, yeah, say they only give you 20 minutes, so there you go. Now, what I want to do here, so the basic theme here is I'm going after quantum theory and claiming that it's really a participatory theory, which is not a new idea. It's, as you'll see, it's been around since Wheeler pushed it a lot and other people, but it didn't go anywhere. And I think the reason it didn't go anywhere is because of the engineer. It's being run by mathematical physicists and not engineers, first of all. And the other part, it has to do with the thermodynamics, which I think is crucial. So we finally get to understand quantum theory, according to this, at least another perspective, if we understand it in terms of participatory systems engineering thermodynamic framework. So now, trying to figure what I'm doing here. Next slide. Okay. So I want to do, I decided to throw this in. It's kind of a preamble for people in systems. I'm thinking a lot of the audience here is systems theory people. And like Wayne and I have had this dialogue in the past about whether systems theory should be understood as a scientific theory or as an engineering theory. And I've been pushing, of course, that it's a participatory engineering theory. Now, one of my reasons for that is the modern origin of systems theory really came out in engineering and operations research and cybernetics. And in practice, for people who practice using systems theory, system design questions are not scientific questions. Design questions are not scientific questions. Another theme in there is that system design is not applied science. Okay, so the tendency to call systems a science comes, I think, from the dominance of the mathematical physics crowd and its unyielding mechanical representation of both quantum theory and thermodynamics. But quantum theory, properly understood, as I will argue, assures us that the ultimate theory of everything, if you like, will not be of the classical mechanical type. What's been missing to get us beyond that is a systems engineering thermodynamics. And per hypothesis, systems theory is a thermodynamic theory. It always has been. Engineering thermodynamics will be seen to be systems thermodynamics. I'm going to say those are actually the same. So, okay. Second preamble. Just so people have been working in systems theory and thermodynamics and what is energy and how does it work, have unfortunately been saddled with or favored, anyway, the Clausius-Boltzmann-Gibbs interpretation of thermodynamics, which is the bad guy, so to speak. Useful sometimes, but not representative of the whole. And for example, Schrodinger's little book, What is Life, goes into this thing. It talks about living systems as consuming low entropy stuff and generating high entropy. And overall, the system is running down. Resources are declining, energy is declining. This is comes out of the Clausius, the heat death of the world and everything, which be nice to get out of, but they don't seem to be getting out of it. Okay, and in socioeconomics, we're familiar with Ehrlich's 1960 prediction, this population bomb, that we will all be starving by 1985. And Vauxhall-Smith continues that tradition, emphasizing resource limitations. Now, so where does this go in the systems engineering thermodynamics program, which I'm trying to give greater foundation to? Ramiz Nam, in his book, Infinite Resource, The Power of Ideas in a Finite Planet, argues that energy policy should be based on not on how much water, air, soil, or silicon you have, but rather on what you do with it. In other words, on system design. So the idea he's saying is the infinite resource is ideas and system design. And that also comes out in William McDonough's great book, called The Upcycle, Beyond Sustainability, Designing for Abundance. McDonough has this great thing. He says, sustainability is like getting up every morning and asking how I can be less bad. All action seems to be unprofitable. As you're always losing, to be alive, so the best thing to do is commit suicide or something, I guess, save the world. And there are people pushing that anyway. Anyway, both McDonough and Nahm are into this constructive emergence model, which is where all this goes, I believe. Okay, so I want to start here, like making sense of quantum theory. This has been a problem for some time. And Feynman regularly quoted this famous quote. He says, if you think you understand quantum mechanics, you don't understand quantum mechanics. And then Smolin picks this up in 2010. He's talking to a group of graduate students at the Perimeter Institute and talking about when he and his generation came into quantum theory. He said in the 60s and 70s, he said we were, the previous generation sort of gave up on trying to make sense of quantum theory. And so we were going to get it. And he says, and it's now 2010, and it's become rather Kafkaesque, which, if you don't know that term, weird, that we have made no progress whatsoever. However, the experimentalists will tell us that quantum theory is the most successful theory in history. And I had a physicist friend he's talked to about this stuff, and he goes, finally we're going through, he loved all the philosophical stuff, and then he goes like, but I don't need to understand it to be able to use it, to apply it, which struck me. And that's, I think, this is actually a real situation. So how can we not understand it, and yet the experimentalists can use it as, the most successful theory in history? That's kind of like, that's been sitting there for years. Okay. So first thing I want to distinguish between quantum theory and quantum mechanics. Quantum theory should tell us about the nature of reality, and that's kind of the big question, the way I'm going to put it. Quantum mechanics is about particular types of application. So the experimentalist can, find versions of quantum theory and derivative, like you want a particle or wave theory or whatever, and use one or the others, and you can apply it. But what does quantum theory tell us about the world? Well, the two-slit experiment kind of captures it, and that is that quantum theory, quantum reality is ontologically ambiguous. Is the world made up of particles or is it made up of waves? Feynman used to say, well, it's wavicles, which is like an answer of nothing. So anyway, you observe in one way, you see particle aspect of reality. Observe another way, you see the wave aspect of reality. And Heisenberg goes on to say, the experimental setup to see particles and the experimental setup to see waves, these two setups themselves are complementary. All right. So quantum theory is not a classical mechanical theory. And the reason is, just off the top, without going into detail, is because it interpolates two complementary classical mechanical theories, Newtonian particle theory and Maxwell's wave theory, electromagnetic wave theory. But how does it include both those theories? Because they're complementary, just like particle and wave are complementary. Newtonian mechanics is and Maxwellian mechanics are complementary. So quantum theory wants to understand reality in a new way, in a way that moves us from the passively observing spectators of objective reality out there to active participants in an historically developing reality. Okay, so my bold hypothesis, the base of this talk, is that quantum theory and quantum reality can only be properly made sense of in a more general post-mechanical engineering thermodynamics. Now, my limited agenda here is not to present settled arguments detailing every aspect of this, but rather to outline a prospective map of a research program. Many of the component reasonings will require further elaboration, and that's why sometimes I run long, is because I try to elaborate, but I'm not going to do that. So, but that's the program. Popper's put forth this idea of a bold hypothesis, and we'll learn the most from bold hypotheses, not these piecemeal things. So this is a bold hypothesis. Okay, so the way I'm going to lay this out, part one, I'm going to identify 4 defining characteristics of quantum theory. These are all pretty straightforward: participatory, indeterminate, complementary, and non-commutative. This is part two. I'm going to develop the engineering thermodynamics of Lazar and Sadi-Carnot, just so you know what it is. It's not the same as the Clausius-Gibbs thing. And then I'm going to point to it turns out that the 4 characteristics that I pointed out in part one of quantum theory are also definitive characteristics of engineering thermodynamics. That's maybe coincidental. I don't think so. But I think that's impressive in my understanding anyway. And then part 3, I'm going to reach back historically to the precursors of Carnot's mature ideas. Earlier insights came from Huygens and D'Alembert, and Leibniz brought these forth in his proposed meta-paradigm shift from statics to dynamics, which is also from science to engineering. So that's the agenda. Okay, I'm going to go through these. These are easy, I think. So the 4 characteristics of quantum theory. Quantum theory is a participant theory. This is, why do you need to have collapse the wave functions up? Because it's a potential theory. It says it's indeterminate. It says, the world is, in order to get an actual world, you have to have, an observation, if you like, or an action. And you need a participant to do that. And so the theory is not classically mechanical, and is not classical mechanical is from one actual state to another unique actual state. It just one to the next. There's no potential. Whereas in quantum theory, we're moving from a potential, which has options, to an actual future. So outcomes are contingent, and contingent on a choice must be made. The potential represents the possibility of alternative futures, not multiple universes. So, and Wheeler's big on this, and Wheeler, a great essay, if you want to look it up, called Observership is Genesis. And this is the participant's act of observation is what actualizes. I don't think it's observation. I think it's an act, but I think it's the act of a participating engineer that actualizes, as we'll see. Okay, second characteristic, it's indeterminate. And this is captured by the idea of the potential, the actual. We see this and talk about collapse of the wave function, but I don't think it's really made clear that what we're moving from is an indeterminate state to a determinate state. Of course, the determinate state is a new indeterminate state, but okay. So in Heisenberg's original terms, he goes on about when he thought about this, the uncertainty thing, he originally favored indefinite and indeterminate. So it's already there. Heisenberg's uncertainty principle is really Heisenberg's indeterminacy principle, saying that, reality is in some sense inherently indeterminate. Now, Pauli, I like this quote from Pauli. He kind of combines 1 and 2. He says, the new pattern of thought, we do not assume any longer the detached observer occurring in the idealization of this classical type of theory, but an observer who, by his indeterminable effects, creates a new situation, theoretically described as a new state of the observed system. Okay, so I think that captures the thing. So the third characteristic is complementarity. I think it's an essential characteristic of quantum theory. Bohr emphasized it. He emphasized that particle and wave phenomena are complementary. They're co-defined opposites. The way I like to think of that is co-defined opposite is local and non-local, which we get in modern discussion of Bell. But the idea of local and non-local, that's 2 different concepts that are co-defined opposites. So, in quantum theory, observables are conjugates, and conjugates are contraries, and contraries are complementary. So goes the theme here. And Heisenberg at one point says, this whole idea of uncertainty is really derivable directly from the existence of conjugate variables. Okay, which is, say, complementary variables. Conjugate variables are a really interesting idea. It was much better developed in modern thinking than it was at the time. This is, Bohr didn't miss this at all. This is his coat of arms when he was inducted into the Order of the Elephant or something like that. And the thing over the top, you see obviously the yin-yang diagram there, but and it's contrary, it means contraries or complementary. Einstein has this nice quote that I like, reality is complementary. He was asked, what is quantum reality? And he says, physics is, of course, an attempt to conceptually to grasp reality as it is thought independently as being observed. In this sense, one speaks of physical reality. Well, right off, you see that he's a spectator model, not a participant model, but nonetheless. And he says in pre-quantum physics, there's no doubt as to how this was to be understood. Newton's theory of reality was determined by a material point in space-time. Now, to understand that, you understand that he's onto this absolute simultaneity. Now, if you have absolute simultaneity, which he accused Newton of, well, the only way you can have everything happening at the same time is it happen in the same place, and that's the material point in space. So that's what he's saying. The implication of Newton's theory is that reality is this point in space. Now, Maxwell's theory, it's basically the opposite. It's by a field in space and time, where every place in space is a different time, every different time is a different space. And then he says, in quantum mechanics, it's not so easily seen. Now, I've gone over this with various people, and the point is that it's these two different, the Newtonian and Maxwellian space-time frameworks are complementary, and they have complementary symmetry principles. Defined by complementary symmetry principles. If you never thought of complementary symmetry principles, think it through. I asked Freeman Dyson about that, and he goes, absolutely. Okay, another way, complementary is not really a new idea, and just to get a sense of it, one thing that the Bohr said was, of course, that all phenomena in quantum theory, all phenomena have both a particle and a wave aspect. We don't have particle phenomena, wave phenomena, as we originally imagined, but we have phenomena that always have a particle aspect and a wave aspect. Okay, now my analogy here is when you observe a soccer game, do you see cooperation or competition? Both? I don't know. Alternatively, can you see them both? Can you see at the same time? And do you see the actions of one player or the actions of the whole team? And is that competitive or cooperative? I think you get this sense of, cooperation and competition are also complementary. Okay, so this is the tougher part. The fourth characteristic of quantum theory is that this new non-commutative geometry. So it turns out complementary variables don't commute. So I'm not going to go into the whole vector calculus, but AB doesn't equal it. So if you go one way through things, so in regular vector calculus, you can go back and forth. And that's your normal calculus. But then when you add another variable, you get to multivariable calculus. And multivariable calculus is not a generalization over classical calculus or geometry. It's unique, and the reason it's unique has to do with this non-commutativity. Anyway, so as a consequence of this non-commutativity, reality emerges selectively and irreversibly. And if that's true, then reality is actually cumulative and irreducibly historical. Okay, if something happens, it happens. It's part of the universe. The universe is cumulative of events, and it's irreducibly historical. So it's always going forward. All right, so I already said this, I think. Well, anyway, here's my favorite mantra here. You can't get here from there. And the reason is, what I'm saying is you can't get to quantum theory from arguments about the limits of the classical theories, okay? Because it's a revolutionary step, just like a Kuhnian revolution. So there's a step from the limits of mechanical theories to quantum theory framework that can't be reduced to mechanical concepts. And that's when the thing's been really tough. And it requires a meta paradigm shift, which I will be talking about. Okay, so summary part one. None of the four distinct characteristics of quantum theory can be understood in any classical mechanical framework, in any framework defined by the presuppositions of classical observer-independent symmetry and conservation.
Hey, Terry, can I ask a question? I know you don't want much time taken away, but
quick, yes.
When you say it's not reversible, we do know that classical theory can, at least the results of it, can, if you reduce down the characteristics of, well, anyway, I guess I don't like your question. I don't like your question, Wayne. Forget it.
Okay, I'm going to go on. So the focus of part two is, I mean, I know what the question is, and I have an answer to it, but I don't, it's too nonsensy thing about microphysics and stuff. Anyway, so I'm going to go on to part two, but in part two, I'm going to argue that quantum theory is a thermodynamic theory. And you already know that in some sense, because you look at Schrodinger's equation, you know, the U is, it's about energy. And in Lagrange is energy, and Hamilton is energy. And so I had a conversation with Brian Greene, and I was pointing out to him, I said, Brian, to sort out modern physics, you need to get a proper understanding of thermodynamics. And he just turned around and looked at me and says, Terry, it's all thermodynamics. Now that shocked me a little bit, but then I realized that he was right, that all of modern physics is embedded in thermodynamics, and it's string theory and everything. So thermodynamics is the king of the hill beyond all these other, sub-theories. Okay, so now our problem is physics textbooks tend to represent thermodynamics in terms of the mechanistic Clausius-Boltzmann-Gibbs formulation. Yet quantum theory is not a mechanical theory in this classical sense. So here then is our problem: how to understand quantum theory thermodynamically without the mechanical presuppositions. The solution proposed in this essay is that quantum theory is properly understood in terms of engineering thermodynamics. Okay, so part two. Doing okay time-wise. So my strategy here is to develop engineering thermodynamics of Lazar and Sadi-Carnot. And in the process, we'll see there are four definitive characteristics of quantum theory are also definitive characteristics of engineering thermodynamics. Okay, so this is my muse. I visit him a couple times a year in Oxford, Peter Atkins. And Atkins wrote this book a few years back called The Second Law. And in that, it shocked me. He said there are two histories of thermodynamics, Carnot and Boltzmann. And he says the Carnot traveled towards thermodynamics from the engine, then the symbol of industrial reality. Boltzmann traveled thermodynamics from the atom, the symbol of emerging scientific fundamentalism. Okay. And then he goes on, he says, thermodynamics still has both aspects. Now that shocked me. I mean, modern theory, there's two different versions of modern theory, modern thermodynamics? Yes, actually. So what is the relation between the current mechanical and engineering versions of thermodynamics? So the Boltzmann, Gibbs version and the Carnot version, what's the relationship? Okay, first of all, it took me literally 3 years to convince myself that Atkins was right, that there are two versions going around. And my insight ultimately that convinced me was that it was the difference between mechanical work and thermodynamic work, which I'll go into a little bit later, but just for a highlight there. So I think one must be a special case within the other, was my thought. So I think that either engineering thermodynamics is a special case of mechanical thermodynamics or vice versa. Okay, so my hypothesis is engineering thermodynamics is the more general, subsuming and superseding all possible mechanical formulations. Now, the other guy who got all this early on was Don Cardwell. And my friend, anyways, somebody kept telling me to go meet Don Cardwell, and I didn't do it, and then he died, unfortunately. So he's on my track here. So he says, almost traditionally, it seems accounts of the development of the concepts of work and injury have tended to describe them within the classical framework of Newtonian mechanics. And he said, I'd like to suggest that this may be to take too narrow a view of the case. I guess so. So Cardwell took a broader view and came to realize that the real history of thermodynamics is about machines and engines. And Cardwell was at the University of Manchester, which was the seat of the Industrial Revolution. So it's not too surprising that he was the one that came up with this. So Cardwell, his great work on UK's Smeaton, who did a lot of work on water wheels. And this is really close, if you get into really closely related to Sadi-Carnot's work on steam engines. And so tracing back, so Cardwell starts then to look at the history of engines and machines. And all of a sudden he realized you go back to Sadi, but then you start going back beyond Sadi. In the 17th, 18th century, there were all these articles or essays being written on the topic roughly on machines in general. And Huygens wrote one, D'Alembert, Leibniz, later Euler, Coulomb, Carnot, they're all writing on machines, trying to understand machines. Well, you don't see this much in the Boltzmann, Clausius-Boltzmann stuff. I don't think, maybe a little in Clausius in the way, but so the concern understanding machines in general did not, I want to emphasize, this concern with understanding machines and engines did not arise from within the mechanics research program. Okay, you look where it came up from engineers. Okay, and this is a point that's made in philosophy, history and philosophy of science along the way, that the whole of thermodynamics really came from engineers, not from mathematical physicists. Okay, so now, what's the real history? So Lakatos popularized the idea of rational reconstructions in the history of science, and this is kind of it. So historians of science, accepting the presupposition of the mechanics research program that, the ultimate theories can be mechanical, interpret the history of science as a history of advances within the mechanics research program. They seek supportive evidence while counter evidence is either ignored or misrepresented. This is, I believe, was resulted in the dominance of the history of thermodynamics in the Clausius-Boltzmann-Gibbs tradition. Okay, so this is I have to read this. So this is I think, early essay of Clausius, and he says, Carnot proved that whenever work is produced by heat, a certain quantity of heat passes from a warm body to a cold one, as to cold sink. This transmission Carnot regards as the change of heat corresponding to the work produced. However, Carnot says expressly that no heat is lost in the process, and Carnot adds, this is a fact which has never been disputed. It is first assumed without investigation and then confirmed by various calorimetric experiments. To deny it would be to reject the entire theory of heat, of which it forms the principal foundation. Okay, Clausius then says, I'm not, however, sure that the assertion that the production of work, and that in the production of work, a loss of heat never occurs, is sufficiently established by experiment. And he goes on, he says, perhaps the contrary is to be asserted with greater justice. Okay, so what we see here is that Carnot and Clausius are speaking different languages here. So Clausius sees the driving force of, heat as a driving force, and that driving force declines as work is produced. Carnot says expressly, no heat is lost in the process, that the quantity remains unchanged, and he adds this fact, okay, so the principal foundation. So I think what he's actually saying, this fundamental principle, this principal foundation, is actually, as will turn out, the conservation of living force of vis viva. And I'm going to suggest that this is the first law of engineering thermodynamics, conservation of living force. No, we don't even know what living force is yet, but we'll get there. Okay, so Lazare Carnot, in his essay in 1803, Fundamental Principle of Equilibrium of Motion, he outlines his project as to articulate an engineering worldview, really. And in his opening remarks, he says, he argues that rational mechanics can't account for engineers and engineering practice. So this is like saying to the mathematical physicists, where are the engineers in your model of the universe? This is one of the things that led me away from the scientific worldview itself. I don't see myself in the scientific world view. I mean, everything's deterministic. I mean, what's inquiry? It doesn't make any sense. There's nobody in and no people there. So the entire mechanics research program, by its very nature, adopts this detached spectator representation of inquiry, and the inquirer is outside the system. No observers, no active agents, no participant engineers inside. So Lazare's engineering world view is participatory. Engineers and engineering practice are natural components of reality. I go on to say that inquiry itself has to be part of a natural aspect of reality. Then Carnot is just the beautiful part. He presents this very specific argument, citing a well-known engineering principle. What we lose in time, we gain in power. Now, way to put it, if I can use pulleys, so if I use a pulley to raise something, it takes more time to raise it, but the unit power that I need to do that is less. Okay, that's kind of what he's saying. So, and we'll see from this one statement, I'm going to go on and develop these four characteristics: participatory, indeterminate, and so forth. They all follow from this one engineering principle. Okay, so we've said the engineers are, you should say, embodied participants. They're part of reality. Okay, engineering thermodynamics framework is a participant framework, what I call Carnot's epiphany. This is we're engineers in a world of engineering. Okay, and another to say we're agents in a world of agency. It's really best in the intro to Sadi's book. It talks about the meteorological cycle and all these other things. All these engineering processes are going on, and we're engineers within that engineering world. Okay, so if quantum theory is engineering thermodynamics, it would resolve a couple of points. These are minor, that, why do we need observers of collapsed wave function? You don't, it's all nonsense, because they're not outside, there's no outside to the system. And it removes Bohr's cut problem. Okay, so, but engineering world, so the other part is Lazar's well-known engineering principle that we lose with time, lose in time, we gain in power, means engineers can accomplish a task, for instance, faster, slower, using pulleys, will be slower, but requires less power per time. Now, the participant, so what this means is the participant engineers have options. This is a key point. They have options, okay? They find themselves in a partially constrained but irreducibly indeterminate reality. Like I say, engineers have constrained free will, okay? They can't do anything, but they have free will within constraints. So Florman wrote this great book called The Existential Pleasures of Engineering. It's a great book. And what he says is he properly connects it to the continental existentialist movement. And his existential engineer has the ability to act, but no definitive script. Okay, actualization is of an indeterminate potential and requires a choice. In other words, one of my engineering colleagues says, I teach my students that they're opportunity actualizers or value manifestors or something. Okay. So anyway, so that's the basic idea. So engineers are not like this idea of applied science. It's not a logical thing. No, they don't know exactly what to do, and they have to evaluate and they have to try different things and they learn and so forth. And solving an engineering problem is different than it would be imagined in applied science. In applied science is calculated, but engineering problem solving is much more complicated, and you have to try things out, and you have little subtests and all that sort of stuff. So anyway, it's a creative opportunity that the engineer finds himself in, a creative opportunity to actualize future reality. And instead of what this ends up doing, it transforms this idea of a probability space that comes out of Schrodinger, and in the engineering worldview, it becomes a constrained existential possibility space. Okay. So engineers are participants, they have options. So Pauli, I already read this one once, and I'll say it again, the new pattern of thought, we do not assume any longer the detached observer occurring in idealizations in this classical type of theory, but an observer who by its indeterminate effects creates a new situation theoretically described as a new state of the observed system. Okay, so third component is complementarity. And this is really what drew me to the connection between Lazar and quantum theory in the first place, this idea of the composition of motion. And the idea is that all motion and change in Lazar and in engineering in general has both a linear and an angular aspect. So you see all the descriptions of motion in Lazar's essays, it always has a cosine angle added to it. So what is that? Why is there always an angle associated with a linear motion? So for him, all motion is composite. So the parallelogram of forces doesn't work in this forces to higher dimension. The parallelogram of forces is adding different linear things together. And that's nice as long as you're doing simple vector calculus. But when you go to this higher order thing, when you're combining linear and angular, or if you like, linear and rotational components, as all motion is composed of both of those, then it forces you into a higher concept of change. So it's not just motion, linear motion, that's nice Newtonian stuff, and your rotation, Newtonian rotation, if you like. But now we're in a thing where they're combined. Okay, so real motion, real change has two components, and they're complementary. And this complementarity goes back to they all trace it back to ancient Greek stuff. So now So change now, since it's a higher concept, we need a new word for it, a new term. And the term that comes up is called action. And I think Lazar takes it from D'Alembert, a little bit from Leibniz and Huygens, maybe. Okay, so complementary to engineering. So one way to put it, this is something that Atkins got me onto. The Newtonian linear motion is by infinitesimal linear steps. So you can see right out of the bat, so infinitesimal means it's derivative, it's a differential. Okay, so Newton is leaving something out. His linear motion is leaving something out. And what it's leaving out is the angular component. And to get the angular component, you needed a whole separate theory of gravity to account for curvilinear aspect of motion. For Lazar, it has both. Okay, and I've already covered that, I think. It's Archimedes. Archimedes, they all trace back to Archimedes' argument that the complementarity of lines and curves, as to the quadrature of the circle and all that sort of stuff, and higher geometry. Anyway, okay, so Lazar reviews the Euler-Lagrange approach, idealization. He said these are useful, but not representative of the whole. Ontologically and methodologically, the Euler-Lagrange principle-least action is ambiguous. It's really about extrema. Euler makes this criticism of what Lagrange does. He said, hey, wait a minute, we're not talking about least action here. Sometimes it's least, sometimes it's most. It depends on the problem, and you can't just, so whatever, you can't say that the whole system is representative of the whole because it's ambiguous, okay? It's kind of like particle and wave, but so the key takeaway I want to get here is that linear and curvilinear mechanical ideals are complementary and taken individually cannot be representative of the whole. The analogy is particles and waves. The world is not made up of particles and it's not made up of waves. Neither one of those can be conceptually representative of the whole. Not to say there aren't particles, there are waves, but neither one of those taken by themselves is representative of the whole. Okay, so so all change has two codified complementary components. I said the search suggested me to Lazar and quantum theory. And De Broglie, this is sort of a repeat. So anyway, the other person who didn't miss this stuff, De Broglie gets it. Max Planck, who was supposedly obsessed by the connection of his concept of action, the quantum action, with Leibniz formulation of action. And we'll see this come up again. This link between Planck and Leibniz, I'm going to develop that further. So that's in part 3, we'll go into that. So the last thing in the engineering worldview is it does have the same non-commutative geometry, because you can see it because you already have the complementary components in there, and complementary components are not commutative. Carnot's other major essay is called Geometry of Position, 1803, and it's really it's an essay on non-commutative projective or perspective geometry. Perspective geometry goes back to the ancient Greeks, and but also in that period, around École Polytechnique in France, there's this guy Gaspard Monge, who was famous for, they say, descriptive geometry, differential geometry. It's really a projective geometry project. And a lot of his followers are Poisson, Navier, Coriolis, Poncelet, and that led up to Poincaré. All those guys endorse this projective geometry as the real geometry. And it's more general than any one of the metric geometries. That's kind of one of the key things we get into. So complementary variables don't commute. Consequently, reality emerges selectively and irreversibly. This kind of repeat. Poincaré actually gives a participant perspective definition of space and time in his book. It's quite fascinating how we define space and time by looking in different ways and moving in different ways. It's all based on action and what we discover and how we all become observers, how we become part of the world as humans and observers and able to do things in the world. And he kind of goes through the process of how we do that. You see that also in Piaget, I think. Okay, so my hypothesis is the engineering framework is more general. So what Lazar has done in this time thing, adding a time dimension of engineering practice, he moves us from the mechanical path-independent thermodynamics, which if you've had thermodynamics, you're familiar with that term, path-independent, to a more general, higher dimensional path-dependent thermodynamics. And path-dependent, then you have to take time and, how fast did you get there? Path-independent is how high or how low did you get up or down the mountain? But in path-dependent, you want to know what path did you take and how long did it take you and what, method did you use? Okay, so two hypotheses here that need a further elaboration. I say, I'm going to claim the second law of engineering thermodynamics was Carnot's principle. And I just learned that Pierre Duhem actually got that. Basically, I'm saying the first law is conservation engineering thermodynamics. Okay, so this is part 3. We're doing pretty good on time, I think, here. So I want to know, like, Lazare is so brilliant. I want to know where his ideas came from. What are the historical precursors of Carnot's mature ideas? And Cardwell noted that historians selectively neglected the popular essays on machines in general in the 17th, 18th century. Now, if you look, I think the earliest person who got all this was Christian Huygens. I'm making a presentation on that was in April, I guess, in Delft. But he gave his results to Leibniz. So where did Leibniz get it from? He got it from Huygens. And this has to do with the compound pendulum and all sorts of interesting stuff that Huygens was working on. And Huygens, I call it Huygens' boat. His theory of relativity is not the same as Galileo's theory of relativity, Galilean relativity, which people seem to be mistaking. Anyway, later players in this, D'Alembert, I think, is very important and certainly important to Carnot. Carnot studied under D'Alembert briefly. Well, D'Alembert was very old, Carnot was very young, but he got what D'Alembert was saying, and he uses a lot of the same terminology. Also, the Bernoullis are in this. Euler, Coulomb wrote articles on machines in general, and Carnot did too. So Leibniz offered the most general vision of his proposed meta shift in his shift from statics to dynamics. So what I'm trying to do here is I'm trying to take all those guys, and I'm just going to try and go after this stuff in terms of what Leibniz did, because he makes this really nice what I call a meta paradigm shift from statics to dynamics. And Lazare actually comments in this in his essay on positions that he's trying to complete Lazare's or Leibniz's dynamics project, which he called analysis situs. So this is a main paradigm shift from statics to dynamics. What's going on here? Because it's from mechanics, science to engineering, not advanced within science. I'm going to call it it's kind of a meta-Kuhnian revolution. Kuhnian revolutions are sort of within science. They're all scientific revolutions, one scientific revolution next. If that's our sense of a paradigm shift, goes a step beyond. This is going to a completely different system. It's going to engineering. Okay. So Princeton's, one of the major players is Princeton's historian of science, Gillespie, identifies the core 18th century issue as a shift from statics, which is, he calls the science of mechanics, to dynamics, the science of machines. Mature Leibniz focuses on engines and engineers, as we'll see. Dewey in pragmatism gets a lot of this stuff, and he sees this meta shift from the spectator to the participant representation of inquiry. I like a lot of Dewey. A lot of pragmatist stuff is, I think, an early attempt at a philosophy of engineering. Okay, so there's a participant ontology of Leibniz dynamics. So I would say it's participatory. The statics worldview is, I like to think of it as a billiard ball world. Everything goes in linear paths and contact causality and everything like that. That's, you hear the particle physicists do all that crap still today. But in dynamics, it turns out it's a world of entities that with internal energy. They're like people walking around, organisms and agents. And you'll see that shift. I'm going to go into details of that. So, and these agents embody the living force, the capacity to affect change. In fact, agents, I've argued, are metabolic engines. And again, I repeat, Carnot's epiphany were engines in a world of engineering. So this whole idea of the Leibniz has what's called organismic engine ontology. There's a great book on this by Justin Smith, collects a bunch of stuff. It's called Divine Machines, Leibniz and the Science of Life. And Leibniz at one point, his later more mature stuff, he goes, like, wait a minute, organisms are like hydraulic pyrotechnic engines. The pyrotechnic is the fire part. Okay, now hydraulics, he sees he sees we can move our limbs and stuff by using hydraulics, which is really in a lot of ways very brilliant. So these metabolic machines are best understood in terms of their final causes. Each part is coordinated for its intended use. I won't go into that. Reality is an engine composed of engines all the way up and down. Okay, and this recalls Plato's same thing. So this engine's all the way down is, something you hear all the time in Leibniz. Okay, so and just for anybody who wants to look at this, I developed this theme elsewhere. If you go to YouTube and search for systems engineering worldview, you'll see something I did a few months ago. Okay, so meta paradigm shift in systems. So Leibniz dynamics is holistic. Okay, and this is where you see the systems theory part. So the shift is from a mechanical, the statics, causal A causes B paradigm. It sort of thing is we talk about, okay, this force hits this body B. Now we want to know what the trajectory of B is. You don't think much about A. A just came in there and hit it. It was something, A hit the thing, and now it has this impetus, it has this momentum, and is going in this direction. And maybe it gets hit again, and then it goes another direction. But so what happens in Leibniz, the A and the B are equally important. So when A hits B, B hits A. Okay, so they're both doing it, and it's a dynamic interplay. So the world is not made up of external causes, A's coming in and hitting B. Like was a problem with Newtonian clockwork. It didn't do anything until God came in and smacked it. Smacked the baby or wound it up. Well, in Leibniz, you don't need any more external causes. Everything ends up being internal. So everything is interrelated. So there are no isolated systems. Okay, so it's holistic. Everything is interacting with everything else. And in this system, you don't need anything external. So change is already, they all say the same expressions, change is already present. Okay, I don't need to account for change. It's just like the world is changing. That's the nature of the world. And it's spontaneous. It's changing spontaneous. Okay, so I'll get a little more. So the complementarity in Leibniz, you think of it this way: in Newtonian, the linear motion has a natural resistance. Okay, so if you just say, in Newton, something gets started, it just goes unless it's hit by something else. Well, that's like perpetual motion. Is that what he meant? Something set in motion will continue in motion unless it's interfered with. Well, where's the interference? I think interference is built in to any practical situation and a natural resistance. Okay, so I think in the practical Newtonian thing, you have both, the motion and its resistance. And the way I like to understand what happened with Leibniz is he enfolds these two. Okay, so this holistic dynamical system and its parts are now composed of complementary, but they use these terms, soliciting and retarding forces. A is interacting with B, B is interacting, and they're dynamically oscillating. They're compensating each other like a natural feedback. Okay, and I was going to go into this a little bit. Huygens has it with a pendulum. Like a pendulum is, going back and forth. It's naturally feeding back. Okay, so this internal energy is composite, and we have to give it a new name, and that's where we get the living force, vis viva. It's this internal energy that has this, from a mechanical point of view, is enfolded. It's a very different world. Okay, so this internal energy is neither created nor destroyed. It's just, he says it's already there. It's already there and it doesn't go away. It's always conserved. Okay, and this is, again, what I call Sadi's first law, which is conservation of living force. Okay, so, and this is important for the systems people. So this dynamic equilibrium is a feedback system, and it leads to this higher geometry. And this is the tricky part. This this movement, the fact that we have to go to a higher geometry, to a different, we're not in a rectilinear space-time anymore. We're not in, in a Newtonian nor in a Maxwellian thing. And this is a tough part. I've been working a lot on this, and I'm not going to go into it, but so think of it as in terms of two different types of equilibrium. The static equilibrium, Newton's third law, equal and opposite, okay? Well, the equal and opposite are linear equal and opposites. In dynamic equilibrium, the A and B interactions are not mechanically symmetric, okay? So, and the term that Leibniz and Carnot uses is that the relationship is transverse. So they have a obtuse and acute angles. I mean, you could imagine, you see it in the diagram in the lower right there of a thing that that the going up and going down are angularly different. And the same with a pendulum. Okay, so what happens is there's a continuous oscillation or cycling of the whole and the parts. A natural systemic feedback system. Each feeds the other. I'll give some examples of that later. Dynamic equilibria are continuous, and they are also net productive. So the image here is the cyclic aspect is the engine. But Lazar emphasizes there's no mechanical gain in engine. Conservation, we're not increasing energy here at all. We're just redirecting it, okay? So, you mentioned before these two symmetry principles, and what Leibniz does in this correspondence with Clarke, he goes after this thing called the principle of identity of indiscernibles. And what he argues is essentially that the Newtonian model of reality has this symmetry and this universality. And he says, the whole universe is, your whole universe is uniform. He says, you can't tell one place from another. Like this, it doesn't make any sense. So things can't exist in that world. And the same goes if you flip over into the Maxwellian space-time. They both have this mechanical continuity. And what he's saying in the principle of identity of indiscernibles is these mechanical continuities or uniformities don't make any sense. Nothing can happen in them. Okay. So he goes then to this higher order geometry, which is a higher order continuity, wherever place and time has both a continuous sameness and a discontinuous. And this is, again, he refers back to Archimedes. So the indeterminacy, I'm switching around here, the indeterminacy in Leibniz really comes with the concept of action. Early Leibniz is concerned to account for contingency. Like, is everything in the world necessary? I mean, like this deterministic thing? No, he says, like, it's contingent, isn't it? And there's a beautiful book by this guy, McDonough, this Harvard guy, and then he points out, he says, he identifies in Leibniz optics, where he talks about the path of refracted light, and he calls it an optimum. And out of this, he develops, which I think is brilliant, if you want to read the book, what he calls a Leibniz principle of optimization. So actions are optimums, and this is where you get best of all possible worlds. It's an optimum actions and optimum forms. Okay, again. So Leibniz defines action as a higher order optimum, a composite ratio of two irreducible ideal complementary components. Action is, in the abstract, is arbitrary or indeterminate. And this guy Tho is quite good, points out that this is then criticized, and that leads Leibniz to this idea of analysis situs, which is to say, yeah, it's arbitrary in the abstract, but in specific situations, there's always an optimum, okay? All right, so then Leibniz realizes that actions are what agents do. Agents are participant engineers with internal energy, with the capacity to affect change, to perform work. So actions, he realizes, are undertaken for reasons. And Leibniz's approach to understanding reality in terms of optimum paths and optimum systems is his principle of sufficient reason. Anything that's happening has a sufficient reason. Anything that exists has to have a sufficient reason because it's an engineering thing. Okay, so I like this guy. This Maupertuis picks up 50 years later on Leibniz dynamics, which had provoked this vis viva controversy. And the controversy was really for the mechanics guys, rational mechanics. They want to know what was the real mechanics. And they, in order to do that, they didn't know what was the principle of conservation, what's conserved, mv, momentum, or mv squared. It was a big issue. And so in Accord, this famous article, Maupertuis gives us animate answer. He says, no, they're both conserved. He says all real change is a composite with irreducible aspects of both mv and mv squared. Again, new concept of change. He comes up with action. He's accused of stealing this from Leibniz. I don't know whether he did or not. Doesn't matter to me. Okay, so actions are optimum balanced combinations of mv squared. Now, and Maupertuis' favorite example, which Euler endorsed, is orbit. So you see here that mv and mv squared form a regular orbit. Now, if you're this old computer program where we used to try and launch satellites, if you're trying to do that, it's really hard because you have to get that satellite at the right velocity, and it has to be exactly the right angle. Otherwise, it goes up and it comes crashing back down, or makes maybe one orbit. So the creation of a regular orbit is hard. And he says it's like the solution to an engineering problem. Repeat that. Creation of a regular orbit is like the solution to an engineering problem. It's for a reason, has a purpose. So Maupertuis then sees everything in the universe as like created by the God, the engineer, if you like. So the structures and functions of reality are dynamic optimizations of complementary components. You can again look at my YouTube thing. Structures and functions of reality are understood in terms of engineering, like reasons. He moves us from causes to reasons, principle of sufficient reason. Now, it's interesting. So this idea of action, historically, it was ignored by the dominant mathematical physics guy. They didn't want to anything about action or anything. They redefined it in, Lagrange and stuff. So this higher order action reemerges in quantum theory. Planck realizes that Maupertuis' action is the same as in his quantum of action. And in this book, it says Planck was obsessed with Maupertuis' action. He later realized that it originated with Leibniz. Now, unfortunately, a year ago, when Mandelstrom wrote this book, a lot of people read, to dismiss Planck's supposed insight and rationally reconstruct the whole thing of action and mechanical concepts of Lagrange. And anyway, they screw it up. I think Planck is right, and I think that he said we should look at, we want to understand quantum theory more, we should look at Leibniz concept of action. Okay, so now I want to give you a couple of examples here. So this dynamic equilibrium idea. So if you look at the Earth, it has two aspects. It's static in one sense. It's homostatic, okay? But it's a dynamic homostasis, okay? And it's been that way. I mean, it's arguable that it's been that way for 3 billion years, 3.5 billion years. And the way I think of this is the Gaia thing. So the O2 and the CO2 work agendas are complementary, and they feed each other, just like with the other thing I'm saying. So they feed each other, and so what is produced? And the argument is that if the Earth is in equilibrium, well, then what? Because there's all this work going on. Well, what the work does, it's an organizational development of the structures and functions of reality. It's not increasing the amount of energy of the Earth. I mean, it's just changing the organizational structure of the Earth. Okay, so the Earth, Sagan and Snyder have this wonderful book called Into the Cool, and basically they argue that the Earth is a progressively developing engine. And it has increasing potential to do engineering type things. Okay, and Tho talks about this a lot. He talks about structural causality. That's what's really involved in Leibniz. So the causality is changing the structure of reality. Okay, and there's a really neat book by this guy, Falkowski, Life's Engines, that the deep sea is a whole deep sea group. And he gives an example of these consortia. So one group of bacteria loves sulfur at +3 and exports it at -5, right? And the other one loves it at -5 and exports it at +3. And they form this consortium and going back and forth and back and forth. And it's kind of a nice little engine. And there's the net process, however, a hydrogen ion is advanced. And when that hydrogen ion advances, it connects to the carbon CO2, and that's how carbon compounds start to get generated. So, and this process of new carbon compounds is changing the organizational structure and function of reality, okay? And Kelsey, This is one rule of being among consortiums: you don't outcompete the others to their exclusion because they're feeding you. You don't outcompete them. And this, my friend Bill Martinez is one of those claim in all this. He's part of this deep sea group. And he says, if Darwinian evolution is supposed to work like a tinker, he says, evolution with mitochondria works like a corps of engineers. I love that. Okay, so just to tie up here, in economics, there's an enigma in economics of what's called increasing returns in scientific economics. So if the scientific description of economies, if the scientific description of economies is appropriate, then the economies should be conservative. So what's this with increasing returns? And then arguably even, we're running out of resources. So what's increasing, how are increasing returns coming from? Okay, but economics naturally produces surplus, okay, progressively, cumulatively, as Romer points out. He got the 2018 Nobel Prize in Economics, increasing capacity to perform work. And Romer's solution is this paradigm shift to engineering economics, which he then terms as endogenous technological change. Okay, and that's very well taken in David Warsh's book. So economic agents are innovative engineers, problem-solving engineers are value actualizers. They develop the world. And an interesting part of this goes back to the consortia thing. In economics, AB is a win-win exchange relationship. Okay, so the fundamental relationship in this is an exchange. Okay, A and B, it's like a trade, I trade you fish for bread. And that creates a new relationship. And every time we create a new relationship like that, it changes the organizational structure of reality. And Romer's realization is that it's in his interest that you succeed. So he says somebody created a new way to make computer chips that's, so my computer chips are cheaper. He said, and I didn't do anything. So he realizes, he said, it's in my interest that others succeed. And I have a book coming out someday, New Growth Economics, New Growth Politics, New Growth Morality. Okay, so that's it. My God, I made it in 60 minutes. Is this possible?